先生们，大家早安！欢迎大家来参加凤山南区扶轮社主办的2023 CAN-FD、CAN-SL 以及 CAN-Open 技术论坛。我是凤南社 Max，
我是 Jessica，
大家好。好。先介绍两位远从德国来的讲师，第一位 Mr. Holger。第二位 Mr. Reiner。待会再由我们的舍友OTO来给我们做详细讲师的介绍。
职业服务是国际扶轮社的5大服务之一，主要是鼓励我们社员透过职业来服务他人，以及实践崇高的道德标准。今年我们凤南社采用一种非常创新的方式来举办，希望能够为我们台湾开启一个新的契机。
首先，我们要邀请主办单位凤山南区扶轮社社长 Jenny 来为我们致辞，请掌声欢迎 Jenny 社长。
有请总监，OTO是我们这次还有2位来宾，大家早上好。好。这个我们经营的非常久，就是我们OTO花了1年时间，所以今天来的会议都一定是收获满满，成就很大。把你们好的都全部吸收回去。对，祝福公司各位公司经营的公司们，大家生意兴隆，昌盛，谢谢。
感谢Jenny社长，请大家再给我们Jenny社长一个掌声。
接下来，我们国际扶轮社3510地区的地区总监也来到现场。总监一直都很关心我们的各项活动服务，让我们用掌声热烈欢迎我们3510地区总监撇出来上台为我们讲几句话。
好，我们主办方是我们凤山南区扶轮社的我们的邱社长。那另外一位我们的专业我们非常专业的是我们的非常资深的我们的洪社员洪启华洪董事长以及我们远从德国来的我们的Holger Managing Director还有我们的 Region CEO 以及在场所有的我们来自全国各地的专业人士，大家早安，大家好。好。我今天是代表我们3510地区这3510地区涵盖的辖区是我们高雄、屏东还有台东3510地区，因为我们扶轮社是用番号、用数字来代表。全台湾有12个地区那我们的辖区是在高雄、屏东跟台东地区，总共有97个扶轮社。凤山南区社是在我们凤山社里的一个扶轮社，我们的社员有45位，非常大家都是专业人士以及我们非常专业的这些社友都集合在一起。那刚刚我们的主持人有提到，我们的国际扶轮这个组织，我们这个社团就是以服务跟联谊为主。我们的宗旨我跟各位报告一下，国际扶轮宗旨在于鼓励与培养，以服务和影响为可贵之事业之基础。第一，我们要借增广相识来扩大服务。第二个，大家注意一点第二个是在我们所有的专业跟我们的职业当中，我们要提高我们的高道德标准，认识一切有助于社会的职业，而且我们每一位社员要尊重自己的职业，借由我们的职业来服务社会，这是前面的两点。那我们的国际扶轮遍布全世界我们总共有遍布大概200个地区跟国家总共有36000多个扶轮社那以地区来讲，总共有530几个地区。那今天我们非常荣幸能够透过这样一个讲座，这样一个我们的论坛、技术论坛， 也透过我们的专业人士啊，就是我们的洪董事长啊，经过1年多的筹划，也邀请到我们非常专业的我们的这个人士来到我们台湾，来跟各位来做一些技术的交流。这是一个非常值得纪念的一刻，非常值得。我们是不是？我要求大家，是不是给予我们洪董事长一个掌声，好吗？那国际扶轮除了做了很多公益之外其实国际扶轮最自豪的就是职业服务就是职业服务。因为我们每一位社员他都有他的专业，我们共同聚集在一起，我们为社会付出。那今天的这个职业服务是哪一个列点？是职业的分享，职业技术的分享。我们职业有职业的表扬，我们有职业的分类，我们有职业的这个分享。今天是做一个最难度最高的一个职业分享，能够得到大家的认同。我是希望今天我们透过这样的一个职业服务，我们扶轮社办的职业服务，能够有这样的一个声望真的是非常非常的感动。那我们希望能够透过这样的职业分享，让我们的社会更和谐大家透过这样的平台，然后我们的国际扶轮做的这样的服务能够深化到每一个职业。在这边敬祝我们这个论坛能够顺利成功。感谢各位的参与，谢谢大家，谢谢。
谢谢总监，感谢总监给我们的鼓励，让我们再给总监一个掌声鼓励好吗？谢谢。
今天会有这样一场技术论坛，还有一群重要的幕后工程，就是我们的舍友 AutoCAD 以及他的公司以晴科技的同仁。虽然他们一直很低调，但出钱出力，忙前忙后，真是非常不容易那我们请以晴的科技的同仁跟大家挥挥手，请大家给以晴科
技的同事们，谢谢你们，
请大家给他们一个热烈的掌声。
文道有先后，术业有专攻。接下来，我们就要邀请我们这位亲爱的 AutoCAD 我们的舍友来帮我们介绍我们 CIA 组织的2位讲师。让我们欢迎我们洪董事长。
让我们掌声欢迎 AutoCAD。
各位业界的先进们，大家好。今天让我应该最高兴的是我最高兴的是我。那因为我和大会讲话，那我首先呢代表国际扶轮商委院地区凤山南区扶轮社，非常荣幸的请大家能够一起来参加这一次的 CAN FAD 跟CAN SL。那这个议题真的是现在最夯的一个议题那我想我在想为什么会主办这一次的活动？是在我小的时候我在修车因为我原本是修车的。那当以前在修车的时候，车子的电线好多，常常把车子的线给压坏。那我们呢，在1992年的时候电子呢发展出第一部车 W140的这部 S Class 的车他就讲这部车呢会减少75公斤的电线，75公斤。那时候呢，就真正的走入了车辆的网络的系统。那之前是各个电脑在处理的，真正的开始叫做网络，而真正的车子的网络是从1992年开始。也因为这个时候，我才真正的在业界大家都，我的专长叫做 CAN。其实 CAN 是什么？其实我今天呢遇到我心目中的崇拜的偶像我在2年前我参加了 CIA， 我跟CIA 会meeting 的时候，那时候我就下定了，我一定要想办法请他们来我们台湾。另外，让我们台湾，其实台湾的资讯产业，我们的学生好多的资讯科、电子、通讯一堆的课程。可是我们这些的课程里面来讲的话，其实在整个车辆的网络的部分，还是比较少人去研究的。所以说我特别举办这一次。那这一次呢，因为时间的因素其实当然我想介绍的 现在两个组长，这个那边是侯个人，他呢是等一下你看他的那个经历的时候，他会去介绍。那他是我真的最崇拜，今天有今天的Ken网的产生，他的立下的功劳，他是这个所有的网络车辆网络的召集人跟 SAE 的主委。那我想大家等一下再听他们的介绍。那我想 Ken 从 Ken CC 就是 Ken 的基本到现在的 Ken FD， 那 Ken FD 来讲的话，解决了 OTA 的问题点，也就像这个烧录的问题，网络的更新的因素 ，EC 的更新的温度。那而 Ken SL 是所谓的Ethernet，汽车的Ethernet哈。那我想在比较技术的部分，我们等一下再有2位的讲。那现在的执行长呢，Mr. Roller 呢，他呢是正在一直的往外的扩充哦。其实，在国际上来讲的话 ，CIA 正在向外的发展。我想台湾会是那个德国以外，现在我们在 CIA 的会议里面，台湾是排名第5哈，台湾是排名第5。我希望呢，我们呢能够赢过这个。我们最少要竞争到第2对，最少要排到第2，因为德国是他本国哈。那我想，我也希望大家今天能够受益良多，今天一定会受益良多的，因为我刚才看过他的简报，里面的那个讲义，去注意一下，有空的时候去看一下，那里面讲的非常的详细哦。我本来以为可能只会讲个历史过程，可是真正的内容，他讲的非常的详细哦。那我想，希望今天大家能够收获良多，真的很感谢各位的来临哦。今天各位的来临，我真的非常感动，因为台湾有这么多的热爱这个车辆的网络这个所谓的这个 Ken 的部分，我们有这么多的同好，那谢谢各位今天的来临，我相信呢，大家会收益良多。那在此感谢各位，也感谢我们凤兰社给我的这个机会，能够有这样的一个机会，能够来看到大家，谢谢各位。
那我们首先邀请我们第1位讲师 Mr. Holder 上台为我们演讲，来，我们请热烈的掌声欢迎 Mr. Holder。
And I will start with the welcome and introduction into the CIA organization. And as said already, I hope that we can create something and also help the Taiwanese industry catch up with Ken XL, Ken FD, and the companies. And thanks to the organizers. It was really 1 year ago that we started the first discussion, and I'm happy to be here, and I appreciated the organization. It's perfect done. So let's have a first welcome and introduction to the CIA. So I will give you a short, very short history of CIA, and CIA is not the American CIA. It's just the same abbreviation, the same acronym. So the difference is the small I. So we have not a capital I. So remember this, don't be afraid. I'm not a spy. I'm not here to do something bad. So I will give also an overview of the CIA organization. And that what we are mainly doing is their technical work. I will also give you information about the structure and our joint marketing activities, and we will then have summary where how you can get in contact with the CIA. But before we really start, I will briefly introduce myself. I'm an electronic engineer that's more than 40 years, and it's close to 50 years, okay. I'm a technical journalist, and as a technical journalist, I initiated the non-profit CIA Association. So there's no company behind me, but it never was. I was just a private person initiating this non-profit organization. I'm a member of the board of directors since 1992, since the foundation of CIA. And you see all the different working groups in ISO, IC, DEAN, SIE, which I'm participating since also about 30 years. And this gives you an idea that I have to sometimes change my hat depending on for which organization I'm speaking. Today I will be mainly at the head of CIA, but also from ISO and other if I'm reporting about these activities. So the CIA Association is a non-profit organization, and it is fostering the image of the cane technology from the beginning. And as Mr. Anya said, in 1992 or 1991, there was the first application in passenger cars, first with Mercedes, then with WM, and so on. It's ongoing in the past that all car manufacturers have adopted CAN technology. And what we are doing, we provide technical product and marketing information to the entire CAN community, independent if you are a member or not a member, to support CAN technology and the knowledge on CAN technology. We give a lot of presentations, not only in Taiwan, but we do this on the daily business. So one reminder, if you want to go fast, go alone. If you want to go far, then you need to go together. This is an invitation for all of you who like to go for a long trip and make CAN a success. Go with the CIA. If you want to have a quick and dirty solution, do it by your own. Just a few milestones. As I said, we was invented or established in 1992. With that, from the beginning, a newsletter, a magazine, because I'm an editor. And if you're an editor, you have an editor. You can't stop writing articles. This is impossible for an editor. So I do this till today, that we provide information quarterly to the entire CAN community, and the CAN newsletter is free of charge. You can download it, and you can get any in-depth articles when you want. So the CIA started already very early in 1992 to develop specifications, and we had to release the very first one already a half year after the foundation of the CIA. And then you see a lot of different milestones, and the last 5 years we were captured mainly with the development of CAN XL and some other things, so that we are still in development with a lot of steps for the, let's say, next 10 to 20 years. So, because we are a non-profit association, we have to follow some regulations, German regulations for non-profit associations. So we have to have once a year a General Assembly. The General Assembly, all members, independent of the size, have one vote. If you're a big company or a small company, you have one vote to elect the board of directors. We have 3 directors. Also, this is necessary to have this to follow the German regulations. So we have a business director. He is leading the business committee with 5 elected members and representatives of our marketing groups. We have the technical director with also 5 other with the same members, and all the representatives for the ITIS groups, and they decide on all technical issues, and they coordinate and manage the sub-layered interest groups and special interest groups and task forces. And the third one is me. I'm the managing director. I do the daily business together with Rainer. And Rainer is the CEO of the CIA GmbH. This is the commercial part where all this CIA stuff is employed. And we do it in a daily business that we have to exchange information, what the members like to have, and he provides with his team the services. The development of the membership is quite stable. We started with very small, with 8 companies only in 1992. And in the meantime, we have moved to 750. I think it's in the moment 761. There are 3 more members in the last few days. It's usual that we have, at the end of the year, we have a lot of new members, and then also some members will quit in the beginning of next year, and then it's another growth. You see, it's still slow, but nevertheless stable increasing of membership. So membership is worldwide spread. However, most of the members, close to 50%, are from German-speaking countries. This is Germany, Austria, and Switzerland. And Switzerland is a very small country, but they have also the same density of members as Germany has. We have strong communities in North Europe, from Sweden to Norway, Denmark, and Finland, and also the others. And you see also that we have some Taiwanese companies there, together with China, mainland, and Hong Kong. To give you an indication which kind of members we have, you see here the business. 62% provides devices, they develop devices. This is something with the housing and you can interface. We have also subsystem manufacturers. They provide more functionality in one subsystem. We also have service suppliers just giving services like training, like development, hardware and software development, etc. Technology enablers, this is what we understand. These are the chip makers, protocol stack providers, and all these kinds, which do not make products which can use immediately. You need them to integrate into devices or into subsystems. Very important is also that we have some tool providers, even if it's just 6%, because everybody needs a tool. And we also have some researchers, mainly universities and government-owned or semi-government-owned institutes. And we have also some software solution providers. And this is the smallest group. We have 3 end users. This is the European Space Agency, the American Space Agency, NASA, and CERN, which is a huge research entity in Switzerland. And let's have a look to the Taiwanese members. It's a little bit tricky because CIA counts where the companies are registered. So when you register as a Taiwanese company in Canada or the United States, then you are counted on Canada. You see Delta here, for example, this has the subsidiaries in those countries. It's not officially a Taiwanese member, even if Delta is, of course, a Taiwanese company. So you see, we have a small group, and I appreciate that we have also then the chance here to get more members and to improve the relation between CIA and the Taiwanese engineering community. What is CIA doing? Anything is focused on the CIA specifications. We are engineers. We are very bad at marketing. We are more focused on technology, to develop technology for the world. And we do this independent of the size of the companies, of the culture of the countries. We do it for everyone in the world. We also, then on surrounding these CIA specifications we develop, we organize conferences like this Technology Day today, or the International CAN Conference, where we support also standardization, and we have applications where we describe what we have developed. We also test things, we provide brochures, product guides, and of course in-depth education, mainly by means of in-house seminars and other events. As I said, technology is that what we are developing. We have the technical committee, and the technical committee coordinates all the developments within the CIA so that we avoid double specifications or reinventing the wheel. The technical committee coordinates the work in the interest groups, and we have 7 interest groups. One is for the lower layers, this is for the more hardware-oriented parts of the CAN technology. The CAN Open interest group is more or less in dormant state because this technology has been developed in the mid of the 90s and is very stable. So we have just to fix some editorial things, and there is nothing to do anymore. There's no new functionality. The new functionality goes into the CAN Open FD approach. This is another, Rainer will talk about this in more detail. CIA also supports other organizations. In this case, it is J939, which is for commercial vehicles, the CAN variant, and there we are supporting this also in the CIA and together with other organizations like SAE, like ISO, plus I will tell you later. Our most activities are in the profiles interest group. There we have for each different industry things developed. This starts from simple things like the motion control and then I/O modules and human-machine interfaces up to the very dedicated ones. Even in subsea, we have some CAN networks with sensors on the ocean ground in a depth of up to 1 kilometer. We have also some other groups working then for garbage trucks, how to make garbage trucks, or we have this for firefighting trucks. We have this the same for medical systems. For nearly any industry where CAN is adapted, we have to provide some specifications so that the products become interoperable. This means that you can buy off the shelf some products, plug them together, and they work. We do this also for lift applications, elevators. So we can buy a car drive and connect this to a host controller. You can also buy doors and they can be connected without any configuration. Of course, this is not only hardware, this is also a lot of software which we have to specify, and then you have to implement that into your products to make really products interoperable. It's not sufficient just to write the CAN interface. And last but not least, we have 2 new interest groups for high availability. High availability is needed in, for example, in outer space applications, satellites, as well as maritime applications where you have a lot of CAN networks in use. Safety and security is an upcoming topic. More and more we have governmental or regional governmental requirements to provide functional safety and cybersecurity. And this is something what is ongoing. We develop these things. We have something, but we have not all the work done today. So just give you an overview on this specification of TIA. So this, you see that we have different series, and each series is belonging to a specific topic. So all the documents in the range of 100, they provide physical layer specifications and technical reports. In the series 200, this is more history. We have developed in the early days the CAN application layer specification. This was, so to say, the predecessor of CAN Open. It was correct from an academic point of view, so it was a very academic approach. But it was really impossible to implement this in software. And then we came up with a more streamlined solution. This is called CAN Open, and very well known since mid of the 90s. This was a European research project, and CIA has taken over the results and made it professional so that everybody can use it. The series of 400, these are the profile specifications which I talked already about. We have the CIA 500 series, which is generally 9 related specifications, and so on. And last but not least, we have the series 1300. And this is for the open application layer. This is the follow-up. So the 300 series for the open application layer. In total, these are more than 20,000 pages of specification. You don't have to read all of them. Don't worry. I have to read them, and I have to double check them. And sometimes we have in these documents really hidden gems, so that means you don't find them easily. But I know where they are, and my team as well, and Rainer's team as well, so that we just send an email and we're looking for a specific function, and perhaps we have it already specified. Maybe under another label, but most of the things are already implemented. So we also provide performance test services. Classic devices as well as can open MD devices. What we don't do, we do not test the chips. Hardware testing is not our business. This is done by third parties. They do this for the automotive industry, and the automotive industry is very committed to request performance testing. On the other hand, performance testing is not really important. Performance testing is just for sales and marketing people. This is like spell checking in human communication. You can use a spell checker, and then you know that your text is correctly in grammar and in spelling. But this doesn't help. Because the other one, I don't know if he has understood. So if I write an email, for example, to my wife, I want to write an email, I love you. And I'm 3 weeks on a business trip. How would she interpret that? It's correctly spelled. Grammar is correct. Spelling is correct. But she may misinterpret that because if you're long married, then you don't tell these nice words to your wife. And she will be suspicious what you are doing on your business trip. For that purpose, we need interoperability testing so that we know that two entities can communicate and understand correctly. So we can do this by means of our global network. So we have some devices which we know that they are correct. And now you can prove that you also can communicate with that, with your device. We also provide plug tests. We do this regularly once a year. So all the manufacturers come together, providing devices for the elevator control systems. And then we know, okay, they can work. You don't test this with your customer, you test it in advance. We also provide a lower layer plug test for the AKN chips. This is in addition to the conformance test. It is necessary to prove that the chips really can work together. CIA is committed to support standardization, international standardization, so we cooperate with a lot of international standardization bodies like ISO, like IEC, but also with the European ones. These are the counterparts, Senelec. We're also working with some national standardization activities, in particular road vehicles and firefighting vehicles, and with the SAE and some others. The activities with DIN, this is an exception. So we learned our lesson in Germany. So this means we write German standards in English language. This is quite new, but we need for that, which we have supported, we need an exception from the board of directors of the German standardization body. But we want in the future that everybody can understand what we are developing. And this is important that we talk in English, and we have to learn our specification in English. Those days when we have national languages is nearly done. So you see what are the CAN-related standards. I have summarized most of these ISO standards which are in the automotive area, and I'm participating personally in all of these activities, and most of the documents are under my control in the related working groups in ISO. So now I have the head of ISO on my head. So we also, as I said, we have also marketing groups. Marketing groups, we are not that good, to be honest. So we have just one marketing group in the moment active. This is CAN-XL. All the others are in dormant state. So they are a little bit lazy, or they have no activities at the moment. This covers brochures, videos, and the interpreters have watched some of our videos to get an understanding what we are doing and how we use the terminology and all these things. We also organize joint stands, and we have presentations like here, and we have also sometimes development of demonstrators. You see here on the bottom the demonstrator for the lift application. We have shown this on several exhibitions all over, mainly in Germany and some other parts, to prove that the products are really interoperable. The International CAN Conference was already installed in 1994, 2 years after the CIA was founded, and we will have next year the 18th in Germany. This is in really very depth the information about the next steps in CAN technology, what has been achieved and what is coming soon. This is not only that we have presentation there. One of the major important thing is that we publish anything on the internet. Publishing on anything means nobody can have patents. This is very important that we provide the information to the public as soon as possible before somebody has patents, because then our small and medium-sized companies would suffer. And this is to keep the technology as open as possible. CIA also protects that what we have developed by means of trade names or trademarks. So we have trademarks for CAN-Open, CAN-Open ID, CAN-SEC, which is the future technology for security, and for CIA, of course, by itself. We also support our members to advertise their products by means of logos. So we have a lot of logos for different things which we have developed. You see here the CAN medical, you see safety, you see all the different flavors of the CAN protocol. You see CAN-Open, which is the standard, the software standard for refuse collecting vehicles, for example. And if you want to have information, you can have the information from CIA. Most of the information is free of charge. So the CAN newsletter can be downloaded. We have the product guides where you find the products which some members provide. We have the monthly. I highly recommend to subscribe to that, because then you will be updated once in a month about that what is available, new information for the CAN community. We have the CIA website. You can visit. We have also a LIN website, because there is no LIN consortium. LIN is another bus system. There's no LIN consortium anymore, but there are many CAN users which also like to have information on the LIN bus. So we support them. We support this on behalf of ISO. We have also a CIA glossary of terms where you find all the definitions, so to get be informed of which terminology we are using, and we describe some of the terms in the CAN dictionary. And of course we have a lot of CIA brochures and to get on dedicated topics. We're participating in fairs. Next year we go into the Bauma in China. We will be on the Embedded World in Nuremberg. Again, also in the SBS in Nuremberg, which is for automotive automation technologies. The Innotrend, this is for rail vehicles, and we go going also to Texas, in the United States, to provide our specifications and information about CAN products and the CAN technology. And for details, you can visit our website. This is my last slide for the introduction. We We learned our lesson from Corona, so we have no more personalized email addresses. We have just that's done project-wise. So if you have like to participate in a technical group from CIA, you go on to secretary@ken-cia.org. If you have technical questions, you can send your inquiries to service@ken-cia.org. If you want to participate in an event, you go to events. And if you want to submit press releases or articles or anything what the CIA can publish, then write to PR. And if you don't know to whom you should write, but just the headquarters, and it will automatically forward to the responsible persons within the CIA organization. So we are not depending anymore on home office, on problems with people which have been infected by Corona or whatever. So you will reach us everywhere. You will not get any information or response out of office. This doesn't happen anymore. Okay, let's have the chance to have some questions up to you. Are there questions? This seems not the case, then I will start with the technical part, if you agree. So first we will look to the KNFD, the flexible data rate, and the status and the future of this technology, what has been done so far. I will briefly go into the history of KNFD, some basic features, some physical layer scalability issues. Then we will go to the KNFD related specifications and technical reports which are available and helps you to develop systems and devices. And then we will look at what is so far achieved in applications in road vehicles and also in other industries. Before we do that, let's have just a few slides to understand what classic technology is and what are the advantages. One of the advantages is the robust transmission of bits. This is very important because if we transport human beings, it needs to be robust and should be available. Otherwise, we can't communicate. So we also need a reliable exchange of frames of information. And there should be a high probability of 10 errors. All this, if you are going by car, or elevator, or aircraft, or a ship, or anything else, this is important for all these different applications. And we need a fault confinement. A fault confinement means if we disturb the others, we should be smart to be quiet. I would like to have this feature also for human beings sometimes. Because if you're in a meeting and somebody is always disturbing the others, it's better he is quiet and goes out of the room. We have standardized lower layer performance test plan. As I said, this is important for some industries. We have also standardized higher layer protocols like like SAE J939 or DeviceNet or others for different models. And what is very important from the beginning was Cane is easy to learn. I can teach you in Cane, in classic Cane, within 1 day. And you will have most of the important information. I can even do it in 4 hours if you have some pre-knowledge, but normally one day is sufficient. And even I told my mother how Cane works, and she was a housewife. And she understood the basic because she is also an expert in communication. Mothers are experts in communication. They communicate with the husband and the children, and they know all these mechanisms. And we have just stolen from human communication the main principles and have just made a technical communication system. And we are all experts in communication, in human communication. So it's easy to adapt this because you're using the same principles and the same methods. One of them is, for example, confirmation of information. And if you confirm some message, there are different levels. If you are familiar with Japanese communication, they always say hi. Hi means yes. They confirm always that they have understood you. That doesn't mean that they agree with you. They just say hi, so I understood. So if I would ask a young lady, do you like to follow my invitation for this evening for dinner? She would say hi. That doesn't mean she will follow me. This would be on another level. Also opposite. Sometimes I don't need any confirmation. I just want that somebody is doing that what I have commanded. So when I'm coming home, I ask my daughter always, please bring me a beer, because you know German people like to drink beer. So I don't want a confirmation. Yes, Father, I understood that you like to have a beer. I just want to have the beer immediately. And this is what we call fire and forget. This is like 10 words. So we don't need, for all these things. We just inform somebody, bring me a beer, and the confirmation is then the task and not on the communication button. So that's how we train people, and it's easy to learn. Low-cost hardware from different sources. This was from the beginning the idea from the inventor of Kane, from Bosch and the others, that any chip maker can provide hardware for a low price. And just to give you a figure, we are selling per year about 2 billion candles. 2 billion. This is a lot. So, where are the success stories? Starts in 1990. There were the first automotive applications, pre-developments, and in 1992, and this was already mentioned, Mercedes was the first one using Kane network in the S-Class, just with 5 nodes. BMW followed then 1 year later with 2K nodes, and then there was into the trucks and commercial vehicles, and so on. This is Kane is still and will be also in the future dominating technology in networking. So as I said, in 2019, the last figures which I have, that was installed in 1 year more than 2 billion K nodes. And it's widespread from automotive, medical, machine building, to really any application. Just last year, I learned that it's also in dentist chairs. In dentist chairs, you have a Kane network. So if you are going to the doctor for teeth, you know, the thrilling is controlled by Kane. You can trust it. Don't be afraid of it. Okay, there are also, I think, limitations, and we are engineers and we talk also about limitations. One of the limitations is that we are limited to 1 megabit per second at about the level of the network. The bit rate depends on the network length, so if you need longer distances than 35 meters, you have to reduce the bit rate. And then you can go up to 1 kilometer without any problem, but then you are limited to 50 kilobits per second. And the other limitation is the length of the data field. That's what you can transport. You can also say this is the payload. And this is the maximum length is in classic 8 bytes. This was sufficient in beginning of the 90s. It was still, this is sufficient for many applications, but we're coming to the end, and some people want to have more than 8 bytes per message or per frame to be transmitted. This was the idea, and to introduce something what is more performant, and this was already done in 2011. So the automotive industry was requesting higher bandwidth for software download and diagnostic, more bandwidth for calibration and universal measurement purposes during the production, and also higher throughput and larger payload for functional safety and cyber security, which is increasingly demanded by authorities. So just a few steps of the development history of KND, which stands for Flexible Data Rate. In February 2011, there was an informal meeting between General Motors, Bosch, and myself, and we discussed how we can improve that. And Bosch started then internally the development of KNFD. It was initiated in April, so 2 months later. And in March 2012, there was the result available at the International CAN Conference. There we presented, Bosch presented then the CAN FD solution. And in 3 years later, we had already published a standard. So this is quite fast. This is only possible that we can, because we want all these things in the style of the ISO, so that we have a smooth migration path from CIA documents into ISO documents. And in 2016, we also published the physical layer for KNFD networks. What is KNFD? What are the differences? The main idea is very simple. So normally in classic CAN, you have an in-bit time detection. This means you depend on that everybody confirms that the CAN has the chance to read the same bit. This is needed because we have a multi-drop network. So there are a lot of participants, and every participant should be within bit time detect the level of the information. If this is a 0 or 1, meaning dominant or recessive. However, after the arbitration, there's only one node which is allowed to transmit. And if only one node, I don't have the requirement for the in-bit time detection. So now I can increase the speed, theoretically limitless. In practice, I'm limited by the technology which I'm using for the transceiver chip. So the idea is simple. I have, after the arbitration phase in the middle of the control field, I switch to the data phase, I increase the speed, and I'm slowing down at the end when all the nodes have to acknowledge the received frame. Because then everybody should say, yes, I understood. And if just one node understood, this is okay for the CAN communication. Then the transmitter knows one of you have understood the message. And I don't care on the others. If the others have not understood, they should indicate this by means of an arrow frame, saying, I did not understood. And then I can repeat, until you reach the level of the fault confinement, and then you go and bust off because I will never understand. And this is then the phase where in the CRC field, then we don't either acknowledge, and we have still then the arbitration phase with the limitation to 1 megabit per second. So we have 4 different formats specified for the classic CAN as well as for KNFD. This means to support even the history. You're backwards compatible by some means. As I said, arrow frames, overload frames are still available. They are transmitted in the classic arbitration speed. And what is also known for those which have some experience, classic remote frames are not more supported in Just a little bit more into detail, you see here that we are now have not only increased the speed, we have also increased the data field. We are not more limited to 8 byte. We have now 64 byte. This is 8 times that what we have. This is sufficient for most applications, for many applications, in particular for control applications where the messages are short. But now we can add functional safety and cyber security measurements. And if you download software, you can also use the larger payload to do this quicker as before. Skip this slide. In classic CAN, anything was simple because it was limited to 1 megabit. And 1 megabit is not that fast. But if you go faster, you have more problems. If you go into gigabyte or whatever speeds, then you have really trouble because it comes to the limits of the physics. And here you see that we have considered just for the loop delay from the transceiver chip to the transceiver chip. This is very easy to achieve. You just can do this by rule of thumb. However, if we increase the speed, let's say 8 megabit per second or something like that, then also the other delay elements needs to be considered. Unfortunately, the chip makers do not provide these figures properly. And even more complicated, modern microcontrollers have here these interfaces, these pins, which are configurable. This means you can do it in a proper way and not proper way, because they might be slow because of price reasons. And if you would choose just this pin, which is very slow, then it will not work with 8 megabit per second. So you have to be very wise, and this means it's a burden for the device manufacturers that they do it properly. In the past, anything was used because the limitation that even the slowest pin was fast enough, but with 8 megabit it is not anymore. So you have to pay more attention on that, and you need maybe some guidelines, and CIA provide those guidelines. How you can calculate this, how you can consider that, even if it is not specified anymore with the hardware. So because you have a choice of selection, and you may choose the wrong decision. So we have detected this all with Plugfest. The Plugfest is a proof for CIA and for its members to prove that the technology is really working. And so we meet, and you see here an example where we are also in Detroit, and there are all the experts from the chip makers are there, and it might also those from Taiwan, where they have transceiver chips or making microcontrollers. They should participate, and then we use real networks from Ford or from General Motors to prove in prototypes that anything is working smoothly. We test that on all the different things, and later you don't need to think about it because we have proved it already. So you see that we prove their robustness and reliability with some very dedicated tests. But anything is then, if this is once done, we have this also in the standards and in the specifications, then you don't need as a user to take care of this. We have done this not only in the United States, we have also done this in Germany. You see here, this is a big group where we have been all the fathers of the KNFD technology, have provided their implementations, transceiver chips, as well as microcontrollers or CAN cores. And we have done also even very not streamlined networks. So we're using just cables. Of course, we will never do this in practice, then we will use always the same cable. But here we have a variety of cables and length, and I think this is a worst case prototype. Nobody will use such a bad network topology. Just to give you a rough idea that we nearly test anything. And so, for example, there's a use case that you need to accept to acknowledge bits for KNFD. We have proved that this is really done by all the chips. And then also the border cases where the shift is in networks, there might be that there's a physical shift of these different bits, and this is also tested and then specified in the ISO standard so that the chip makers can follow them. And still, we have proved that the products are interoperable. This is one of the slides for the robustness proof that we are also allowed shifting by physical effects, which may happen, and you as a user, you can relax because we have tested in advance so that you don't have to deal with that. edge shifting is one of lengthening bits or shortening bits. That is all what we test before we go into the on the market with the products. So what is available for KNFD? You'll see that it's standardized since 2015 or 16 for the KNFD protocol, and also with the conformance test plan, the transceiver specification, as well as conformance test plan. We have a transport network layer for automotive industry, standardized in ISO 15765-2 since 2016. We have updated the KNFD diagnostic individual link connector. So it's not only that we are talking about the protocol, we also have done something for the real connection between the external test tool and the individual networks. And we are updating this currently when we are going to KNFD Lite and to the KN6 transceiver. I will explain this in the next slides. This will be is already released as a draft international standard, the final draft international standard, and will be then released next year. So anything is smoothly going on. KNFD Lite. KNFD Lite is a special dialect for the KNFD protocol, and this is used in automotive applications required, for example, for rear lights or for other devices which provide a lot of sensors or actuators. And you'll know that the new LEDs rear light, they have several hundreds of LEDs to control. And you don't want to spend money for that. And this is why we avoid that we have oscillators necessary, and we have reduced this commander responder behavior. So this is just a subset of the functionality of KNFD, so to make it cheaper for those applications which have a lot of sensors or actuators, like with LED lights. You can also use this for heating, ventilation, and air conditioning systems, etc. In industrial applications, we see maybe a need for KNFD Lite in elevator applications. All the push buttons which you have on all each of the floor. This could be also an application, but this is still under development, and I think also next year we will see the first products from Texas Instruments, from other companies as well. So the basic features, you can read this. The slides will be handed over to you, or have it already, then you can look at it in more detail. So CIA, because we have submitted all our documents to ISO for international standardization, so we just what is still in the CIA. There are some related documents, mainly something what is not standardized in ISO. There's recommendations, development tools help you to design your network. So we have the kind of motor shock specification. We have some physical layer implementation guidelines where you can, if you build a device, then you can read this specifications or these guidelines how to implement this in your devices. We have the protocol controller interface, which is very important. I will tell you in the next slide why this is important, because the ISO is not sufficient on this to make real systems working. And we have design recommendations, and we have just the CIA 601-3 and 601-4 tools. These are Excel sheets to support your system design. They will be updated in the next few weeks. And we have a cable specification. This is important. In classic CAN, you can use any cable. It works. But if you go into higher speeds, then you need more symmetry. And you need also to avoid that ringing on the bus lines. However, the cable, if the isolation material is not good enough, then you have a drop in the impedance. And you know the impedance, if you have a mismatch of impedance in different parts of your network, then this causes reflections. And reflections makes trouble. And in For example, for NMD, using specific cables with a specific isolation material features. So normally, if you have used your cables in minus temperatures, the impedance decreases. And if you have a bad cable, it decreases to 30 ohm instead of 120 ohm. And this is a big mismatch and causes a lot of reflections. So look to the cable and look to the cable manufacturers if he claims to be compliant to the CIA 601-6 specification. If he doesn't do so, then you can check his data sheet and look if he is fulfilling this by yourself. To be honest, if we go for the SIG transceiver is a transceiver which suppresses ringing. This is quite nice idea. Because as I said, you have ringing because of the topology of that cable. But you can reduce the ringing by means of the SIG transceivers because they adjust dynamically the impedance. And if they do so, then you can use not so optimized topologies as well as less expensive cables. However, in this case, you should consider that you are limited to about 67 bit rate, kilobit per second. Here is the point where you stop. You can't achieve 1 megabit. This is nearly impossible. You have to limit yourself, and most of the people are doing this because nobody goes to the limits. Very rarely, I think most of the people will use 500 kilobit and then be on the safe side. So common mode specification, if you're using common mode shocks to have some physical effects avoided, then we have also specification for that, so that you can protect your gain interface. What I told you already in this, you see here what are the bit timing is the most critical part. ISO requires a minimal range in this field blue one, and but this is not sufficient for real applications. So if somebody would just implement in the microcontrollers or the pin controllers this minimal required range, it will not fit your application. So we have then recommended a much larger one range, and you see the green part, this is why it's green. The green is CIA is green, and so it's also recommended part is green. And this is that what we recommend from the chip makers to provide. So what is in the standard is nice. It works for simple applications, but if you have more challenging applications, then you should look that the king controllers support this recommended range. So also you have to measure the asymmetry. As I said, if you go into faster speed, like 8 or 10 megabits per second, then you need to measure the asymmetry. And here's a proposal how you can measure this without any problems. And then you see that you can connect this. You see also that there's common mode shocks and where to connect then the measurement for all nodes and the trigger positions. Cable specifications, I mentioned this already. We need to have an impedance from 120 maximum and minimum and a maximum of 140 ohm. And PVC-based wire insulation material does not meet this requirement. So don't use PVC cables. And there are also a lot of other things which we have specified, and cable manufacturers have to follow this. There are also other connectivity-related specifications in the meantime from ASAM, via SAE for commercial vehicles, via the automotive industry from SAE. They make recommendations how to use GAIN, and depending on the application, you should consider one or the other of these documents. Where this is used, Mainly it's used end-of-line programming. This is done by means of the ISO transport protocol and the diagnostic protocol for calibration of ECUs in the production of cane and then also in the final test of rotating goods. And the reduction of time to do this is important and really saves a lot of money. You can expect if you can download the software much faster, then end of line, you don't have such a long standstill of the different cars. You can do this more quickly, and this saves really money. Second use case is safety and security. As I said, it's increasingly demanded by authorities, and we can now use additional security measures and function safety measures within the frames to support those requirements. Longer process data is also sometimes you need to put into one frame. This can be done by when you have 8 times now the capability or the capacity of the classic can. And we can improve, and Rainer will talk about later, how we have improved CANopen to use it as CANopen FD so that we can make use of the larger fields and that we can have a lot of improvements also on the application layers of the software. Where it is used, Ford and General Motors have introduced CAN since 2019. BMW and Mercedes and Volkswagen use CAN too. Nearly all car makers in India have applied CAN networks, even in China and Korea. They all use it, but mainly they use it 500 kilobit in the arbitration phase and 2 megabit in the data phase. This is what is in the moment implemented, and we have then also the first car makers migrating to a CAN 6 transceiver. This will improve those transceivers which provide the possibility to suppress ringing, and this is, I think, in the next year this will be the next step, and then we can achieve up to 8 megabit per second in multi-drop networks. This is quite a good figure already. Heavy-duty vehicles from Daimler Truck and other OEMs, they have implemented CAN networks running also at 500 kilobit per second and 2 megabit database, and in the future more classic CAN networks will be migrated to CAN FD using SIG transceiver. This is a clear trend. I think in 10 years we will not see any classic CAN application automotive EV networks. Non-automotive applications, this industry which is slower. I was surprised on that. The adaptation of CAN in non-automotive is still slow. CAN is mainly used in proprietary, deeply embedded networks, so we don't see them, we don't know it. For example, in drones, in automatic guided vehicles, in autonomous modular robots, and there are some CAN shields. This is a hardware for Arduino-based solutions is available. I was surprised that this is heavily supported, and there's a migration from CAN Classic to CAN FD, but even this is still slow, but will increase in the future. We have some indications that more and more people are going this way. And there are some investigations already done in CAN for CAN in maritime electronics and in refuse collecting equipment, and maybe others which we don't know. Even if we know a lot, we don't know all the secret developments in the companies. Yeah, so far giving an introduction to CAN, so that you see this is the next step. It is already happening in automotive industry, and in other industry it's close to be realized. And this should be supported by different device manufacturers. Our questions? Here. No questions. questions. Okay, we can have the questions during. Oh, there are questions. Okay. If you speak in English, I can hear yours, but I can give you also the microphone. I can.
Thanks for your presentation. I learned a lot. This 10FD Lite, you mentioned is very price optimized. I'm curious about, do you have a brief description about the competition between the 10FD Lite and the Lin Bus? Okay, thank you.
The Lin Bus is working very close from the communication functionality. It's also a command or responder behavior. But KNFD Lite is much faster. We can go up to 1 megabit, and Lin is slower. Okay, this is one of the differences. And we have a payload of 64 bytes. Lin has not. These are the two new steps which we have introduced, faster and more payload. And Lin will not be developed further. There is no indication that somebody is improving the Lin bus. Might be that CXPI, which is a Japanese approach, is also internationally standardized, is a competitor, but it's only used by one automotive car maker. It's only Toyota. Toyota has developed this CXPI, but it's not used by Americans or European car makers. But they use the CXPI. And the KNFD Lite will be used by American and European car makers. We are a little bit behind the schedule. It was originally intended to have this available by means of products last year. However, the standardization introducing this was delayed a little bit. So we expect that the standard where the KNFD Lite is really described and specified will be available next year. And then the chip makers will follow. We have indications that STMs, ST microelectronics, as well as Texas Instruments have already pre-implementations available. And theoretically, you are not limited to 1 megabit with KNFD Lite. You can go faster, but there are no implementations at the moment. The specification itself doesn't say anything about the speed. You can go for any speed. So let's say, if you would use the SIG transceiver, then you can go up to 8 megabit. However, I don't believe that in this very moment there's a need for that. And this would also increase the costs. And this is KNFD Lite will be, I think, limited for the next few years to run. But this is much faster than the Lin bus. Okay.
Yeah, thank you very much.
There was another question?
Okay, one question talking about the functional safety and the KNFD, which CL level it can achieve.
Functional safety is, the automotive industry have a standard, but they have not standardized functional safety. It's mainly OEM specific. This is a trade-off which we have. We have for classic Canon, we have a functional safe solution for Canon, and there's also a functional safe solution for SAE chain and Line available. Both are more or less outdated. The big problem with all functional safety applications is that the automotive or the industrial functional safety standards, they reference other documents, and these documents are changing frequently. And if these base documents are changing, you have to adapt your specific, and this is a nightmare. So I have seen that for Canon safety, for example, that we reference 3 different documents. And these documents are changing all 5 years. This means after 2 years, you have to adapt, but you have to change your document with reference, and this makes it very difficult to keep anything stable. And if you have developed something, then it's already outdated. This is not politically, this is not acceptable for the industry, because it's very expensive to develop, to change your entire development team for functional safety. You have to change your company, so to say, your development process, and then you have a function safe. It's not only the protocol. The protocol is simple, but the process is that what is behind. This makes it more complicated. And then you have achieved a certificate by an authority, and it's outdated. And then you start again the development, and the same happens again. So this is very critical. And we have developed, for example, can open safety in the year of 1999. This is more than 20 years ago. Of course, we have in the meantime another understanding of function safety, and we have to support soft errors which we have never known that they exist in 20 years ago. So this is tricky.
Okay. Will you introduce cybersecurity for K-Open today?
We're working on this. Okay. Cybersecurity is something different than function safety.
I see that.
Even that is a problem. We have in many applications, we have the requirement that we have to support function safety and security. For function safety, I'm not allowed to change the software because it is accepted by the authorities. If I'm implementing in parallel also cybersecurity, I must change the software whenever I was attacked successfully. And this is also a problem. Because then we have to change things, and we need a new certificate. Okay. Other questions we will have during lunch break or after the show. Okay. Rainer? Okay.
So, welcome also from my side here to Taiwan. So, thank you also for the honor being allowed to talk here, to be here. And I have now the honor to introduce to you Ken Open. So, I was told it's important here to the Taiwanese community to inform you on Ken Open. So, maybe I can have a short hand sign. Who is already familiar with Ken Open? Who has worked already with Ken Open? So that I get a small impression about it. Just raise your hand whether you have just worked with it already. Oh, this is just a very small community. So maybe we can improve it a little bit and can improve and increase the knowledge of that. First of all, as I've already been introduced by Holger, I'm Rainer Sitzmann. I'm the General Manager of the CAN Automation Office in Nuremberg, in Germany. I'm working very closely with Holger and try to assist with my team the CAN community in the best way, in the intended way, in cooperation with Holger. So all the rest you will have done the slide sets, and we accelerate a bit here with the topic. So yeah, Ken Open, we shall introduce Ken Open. It's for those of you that are not familiar with it, what means Ken Open, what is the difference between Ken and Ken Open, we are often asked. And it's like Holger already said, it's all about communication. So he says his mother-in-law understood him very well, and immediately, okay, what was meant. So I experienced it a little bit different. So my wife told her stepmother, my mother-in-law, well, my man, he's working something with buses, he's working with canvas. So for her it was apparently, okay, he is selling a public means of transportation. So this is what communication means. You have to be very precise, you have to be very precise in how to interpret something, and we are doing this now for the CAN communication, that devices can talk to each other, can share information, and therefore we bring to the public one mean, and this is the CAN Open language, how to speak CAN in open systems. How to give devices a certain degree of interoperability,
And you see here the history of Can Open. So Can Open has been pre-developed in a European research project, the ASPID project, I believe by Bosch. And then this result was handed over to Canon Automation for maintenance and further development. And you see, with regard to the date, it was necessary very early, already in January 1995, we had a version 1.1, and a very, as already said, academic approach, academic name, CAN-based application layer-based communication profile in the version 1.1. So also from the marketing aspect, not very well suited, and you see already in the September of the same year they came up the version 2.0 with a more attractive name, a more compact name for marketing purposes, the Can Open. So as Holger said, we're not that good at marketing, but I think this term is not that bad. So it describes very well that this is a mean to establish open systems to give devices a certain degree of plug-and-play capability. Of course, when you want to have now Can Open, you can download it from Canon Automation's website, it's very convenient. And if you do it so, you're not getting this version 2.0, but you're getting the version 4.2, so we have improved Canon Open specification, did some maintenance. And also, as Holger said, we are very willing to support international standardization, so we have submitted the Can Open specification 301. This is the document number of the Can Open document. We have submitted it for international standardization on European level. And you see here, it's now equivalent to the EN 5325-4 in the version 4.0. There are small extensions now available in our latest edition. For political reasons, we haven't updated the international standard, but in general, everything necessary is covered also in the international standard. Then Holger has already introduced now KNFD in brief to us. So there exists also in Canon Automation a community that says, well, we are Can Open users, but now we want to benefit from CanFD, from the improved capabilities of the Can Data Link layer, also from the perspective of a Can Open level, and therefore they updated Can Open. The first edition has been available in September 2017, the document 1301, and we have now the extension to Can Open, CanFD. Introducing not also services capable to run frames longer than 8 bytes, but also introducing new functionality. So Can Open had been developed in 1993, 1994, 5. So the available resources on the microcontrollers have been completely different than they are today, and therefore we can also think today about more comprehensive functions that assist system integrators, and therefore we could consider this when we develop Can Open FD. And just recently, this month, we have released the version 1.1 where we could remove some first ideas that we said, now has shown in first experience that we should do it a little bit in a different way, so we have a slight update of the Can Open FD specification, the version 1.1, just a minute of that. So that. Now, with regard to Can Open, I don't want to go away too long with history, but you see here in 1994, very early, some prototypes have been connected on the Hanover Fair, then very soon first commercial off-the-shelf protocol stacks have been available, so first devices, and then we have learned Can Open introduce a kind of device architecture, gives you a very good idea of how to use the CAN frames to communicate diagnostic data, process data, configuration data. But Can Open, the basic specification, gives you just little information about the data content, which data you like to communicate. And this data content is added by so-called device profiles. There is an I/O that you maintain the status of the first data you input. How can I hand over to an electric drive a control word? How can I get in a harmonized format the status? What is the drive currently doing? All this information is defined in SIA device profiles or for entire applications and application profiles. And this, we add by these profiles, we saw very soon that this is important, this is a really added value for the users.
Furthermore, as it has been already mentioned, there were put some requirements on safe development communication, so we developed here a open safety specification, and as already said, we are very willing to submit our developments to international standardization bodies so that a big community can benefit from these documents. Yeah, one of the, I think, most comprehensive open specifications or standards is that one, that for the rail vehicles, you can see 61375-3, how to communicate with open in coaches, in consists. There we have the basic open specification, network management, remote access to open networks, redundant communication, flying master applications, so all this is integrated. And there's also some activity I like to mention after, I think, about 10 years of really stressful specification work and standardization work. We have now international technical specification here, the open communication for light electric vehicle charging in public spaces. So this was somehow a mess for political reasons, but nevertheless, I will say some words during this day about the standard and about the content, so that you see, okay, also in light electric vehicles, we have a certain share the possibility to use open communication. What is open communication? So we have already seen open is specified in the document here 1. But it's not a single document. Open is pretty scalable. Open just summarizes the basis and provides a fundament in document CR301, but provides also a lot of add-ons. So if I just want not to manufacture a simple device, but a device that is capable to start up a open network, to double check are all devices available, are they configured in the right way so that we can start operating with the application. Then we have their documents 302, when it is important to have reliability, high reliability, then we find here also redundancy concept. What about bootloader updating the firmware of the device over the network? Also here we have in the document 302 some ideas. We will learn that open introduces node numbering. Open devices have a node and a network-wide unique number in our application. So how to apply this number? This is open. So one mean could be that you have a central host controller, and the central host controller provides the node numbers to the device. Also here is an extension. Tools such as conformance test tool, configuration tool, diagnostic tool, they have to learn what kind of device functionality is provided by a open device. Therefore, we need technical descriptions. Host controllers need to know which functionality is available in my system. So therefore, such an electronic data sheet is specified in the document 306 or based in an XML format 311. Then they are used to provide information to the host controller, which information is available, how can we set up our proper working control system. I think also of interest is document 309. How can I access from an external point of view? So for example, from cloud-based services, deeply embedded open networks, how can I get any data element that provides really interesting information for cloud applications? Network access services are in the 309 document. And with regard to light electric vehicles, those are based on the document 320. It specifies the combination between a generic open device and power management functions, some sleep mode handling, these kind of things, they are provided in the documents here 320. So some extensions to the basic open in the number range 300. The number range 400 provides then the aforementioned device and application profiles. What is the application-specific data for a single device or for the entire control system? And this means, as Holger has already said, you don't have to read all the documents to become an open expert. You can just pick those documents that are relevant for your application and you can leave the rest away. So open is very, very scalable. This is, on the one hand, a big advantage. You can tailor the protocol stack, the result of your implementation of the protocol directly to the available resources on the hardware platform. The other way around, this makes complex, it can often sometimes a little bit complex, because you have always, when you select the device, to double check, are all those functionalities supported that I need for my application. Why do we have this big amount of Canopy profiles? This is because Canopy has migrated to a lot of application fields. The scalability of Canopy allows Canopy to migrate to a lot of application fields, and Canopy has been designed for embedded network, modular machine control, linking the machine module together, allowing the information interchange, but it's not limited to this. We find Canopy medical application fields, patient beds integrating more than 25 nodes, so for active care, integrated operating groups, contrast media injectors, talking Canopy to the imaging device. You find Canopy in building automation, so building door control, lift control. We find Canopy in renewable energy applications, solar power plants, wind farms or condition monitoring for pitch control. And we find Canopy also in strong CAN niches, so CAN marks, so like construction machineries. Here, typically in the superstructure part, truck-mounted applications, so truck-mounted working platforms, truck-mounted cranes, concrete pumps, and these kind of things. Or I mentioned already refuse collecting vehicles, but all here we're using Canopy. In ship control, maritime applications, where they can open as used also down in the deep sea, in huge sensor networks, where the oil drilling industry is monitoring what's going on around the drilling hole. We have some oil leakage, we have some seismic activity. Where Canopy is traditionally a little bit smaller is the automotive industry, that we typically operating with closed networks, not open networks. But also here we have some niche markets, for example, special purpose cars, or in light electric vehicles, we find sometimes also Canopy applications. Just for those of you that are not quite here, where is Canopy inside, what needs Canopy, just a small slide, just sorting in what needs Canopy. Canopy is just a specific type of using the CAN frames. So, as Holger indicated with this proverb where he was saying, well, if you want to be fast, then do it alone. It applies also here for the CAN communication. Just do something and you can set up your network. And often then, we have discussions with people, with CAN users, saying, well, I just use this frame for that purpose, for communicating with control world, I use CAN frame 2 for getting the status CAN frame 3. Why do I need this entire Canopy? And I can exactly follow this proverb and I can say, yes, you're right, you can start in this way very quickly. But what about integrating third-party products? They don't have your interpretation available. This brings you the effort to do some integration, some remapping, some modifying of data. And this you will have all the time if you want to purchase third-party products, off-the-shelf tools and so on. They don't have your understanding, your interpretation of the CAN. So you can compare this to the language. We see here slides with Latin characters providing English language, one common understanding here. We could also say use the Latin characters for German, Italian, so most of the European languages are based on Latin characters, but we have to agree on one for having an understanding. And here Canopy is one standardized communication for embedded communication on CAN-based systems. So, Canopy is just a specific type of using CAN. We have there in Canopy several services. So, Holger has already introduced, we have broadcast communication in CAN. This is a very interesting group for communication, for sharing process data, sharing the sensor value in the system. But if I want to do some configuration, I want to have not this mentioned buy and forget, but I have a confirmation that an intended device has accepted the data correctly. And therefore, I need another, maybe a client-server connection. or I want to have some specific mean of communication for network management related tasks. So therefore, can open introduces something that we abbreviate as communication object. We allow to set up in CanOpen so-called communication coherences, like you know it from your cell phone. When you dial the number, you have a direct communication channel to your communication partner. So that in fact, if you have a technical view then on this communication, then you will see, okay, my voice is then transferred in IP packages to an X-basic station, and then via World Wide Web or wherever, and to the cell phone of your communication partner. And the same we have here, we have our communication services. For this CanOpen level, we do not see anything of intent details. They just don't care. But in fact, of course, for diagnosis, for configuration, we need to know, okay, how is such a CanOpen communication object represented on one or several CAN frames, and furthermore, how is a CAN frame transmitted bit by bit in certain voltage levels of the node. So, when we're talking about CanOpen, we are on this so-called application layer. Nevertheless, also CanOpen has some ideas about the lower layer implementation. So, how does this lower layer look like for CanOpen? So, CanOpen has been developed in 1994, so I cannot say anything about the latest physical layer developments. So, it more or less relies on the physical layer as it has been introduced in the ISO 11898-2 from the year 2003. So in these days it was called the high-speed transceiver, capable to run 1 Mbit. But this is just an expectation. As I said, CanOpen is very scalable. CanOpen left always the door open to use other physical layers. So we had already the request to use the deep sea water as physical layer for CAN communication, for huge sensor networks in the deep sea. So also such experience has been done, but of course the main market, mass market, is that one, the ISO 11898-2. But if you have, for example, the requirement of some tolerant communication, this is done, for example, by the oil explosion industry, that transceiver is a small niche market, and they say, okay, we take the advantage of the fuller CAN transceiver, despite we know there's then a problem in getting experience and getting recommendations and getting tools and so on for this niche market. So the mass market, 11898-2, they have built some extensions in the past, so partial networking, low power mode, so they have been introduced by other international standards now, or everything works in the ISO 11898-2 that is used for CAN physical layer. Furthermore, CanOpen has some ideas about the connector. The CanOpen connector does not exist, but for allowing CanOpen devices a certain degree of interoperability, of plug-and-play capability, it's important that you agree on a pinning if you have selected a certain connector. So therefore, connector pin assignment you find now in the document CR106. In the past it had been the degree of ES1. There's that document which provides now just some table and topology recommendation. What about the topology for CanOpen networks? CanOpen assumes typically some line topology. So you have a CAN high line and CAN low line according to the high-speed physical layer, and between the CAN high line and the CAN low line, you evaluate your differential voltage. So the line is terminated with a resistor 120 ohm at both ends. So as already mentioned, it should be the impedance matching connector. To keep things simple, it was said, okay, put 120 ohm resistor on both ends, and then you should have no effects with the reflections. Everything should work smoothly. The devices themselves, they are connected via unterminated stuff, so we don't have to deal with termination resistors here directly in the devices. Be careful, sometimes there exist devices where you can switch on and off the termination resistor directly at the devices. In this case, if you add some new devices, you may change the resistor behavior of the entire network. Therefore, be very clear, okay, make your termination resistors at the end of the line, and then no termination resistors here, you don't have any issue. Often we are asked, why do we have here a further ground line? Why do we need that one? This is just for protecting your transceivers. So this means in some applications you cannot guarantee that your entire application resides on the very same potential ground level. And to protect the transceivers from two huge voltage gaps, you have a clear reference level between the can ground. If you can guarantee that the entire application is on the same ground, no problem, you don't need it. Furthermore, if you would have seen such a picture for a CAN, then you can say, okay, I can add any amount of devices to our CAN network because CAN does not limit the amount of devices to be networked. Can open does, at least by means of the node number that is introduced. When I can open network, you can integrate up to 127 devices. This limit comes from the node number. This is in the value range 1 to 127. Further remark with regard to the physical layer, what are the bit rates? So Olga has shown some slides where you deal with the bit timing in CAN. We want to free device manufacturer system integrators from all these details. We just say, okay, there are a couple of bit rates, just select them maybe via dip switch, via rotary switch, and we see here, these are the CAN bit rates. And you can just select them. They are defined by the CAN specification, also the bit timing behind is somehow recommended by the CAN specification. And we have once again the scalability of CAN. It says, okay, one of these bit rates has to be supported, or the others can be supported. So take care that those bit rates are available in a CAN device that you intend to use in your application. And as Holger has already mentioned, there's a dependency in CAN-based systems between adjusted bitrate and maximum achievable network length. The higher the bitrate, the smaller gets the possible reachable network extension. This has something to do with the bit timing. I like to recommend here in CAN devices, choose the sample point at 87.5% of the bit time. So all devices in the best case should do so. So if you follow this recommendation, then you have the possibility that you shouldn't have a lot of trouble with the physical layer. With regard to node ID adjustment, as I've said, CAN demands a node ID for every CAN device. How you apply the node ID, CAN just don't care. One are the layer setting services. The layer setting services say, okay, there's one central host controller, and this host controller distributes the node ID to the devices. If you have the possibility that there's an engineer around who has CAN knowledge, who has system knowledge, then he or she has already the possibility to use maybe local dip switches, doing it very simply. There's one thing that you shouldn't do, which is that one, assignment of the node ID via the object dictionary. So what is an object dictionary? An object dictionary is a device internal CAN database. So it's the place where a CAN device maintains and administers its data. And therefore, in this object dictionary, there exists a data range, or an object range, where devices can maintain data according to the wish of the manufacturer. There are no CI rules or rules from others that interfere, and therefore some manufacturers say, let's use this manufacturer-specific range to administer a node ID or a bit rate value. Well, this is not the best idea, because this may happen that these devices come with the default settings. You can adjust your new node ID. Maybe the device comes to a node ID 1. You say, oh, I don't need the 1, but I need the 5. You put the device into service, and then comes for whatever reasons the command restore the manufacturer settings, and then the device comes with the old low-rate value. This may cause troubles in your application, and if you do handle the same with a bitrate, you have no chance to run the device ever in the system. In one CAN-open system, only one commonly agreed bitrate can be stored, otherwise the communication fails. So it can now cost a lot of effort and money to dismantle the device from this system, to put it in a reference system, and to reconfigure it. Therefore, we say do not configure bitrate and low-rate via the object dictionary. I have already mentioned the CAN-open connector does not exist. So, nevertheless, we have now this latest document, 106, and here you find a lot of connectors and a lot of pins that provide for these connectors, and then you can just follow this and say, okay, I have chosen for whatever reasons this type of connector, and therefore I follow it. Let's go over a higher data link layer. What are the implementations? It's very simple, it's just CAN. So we are using the CAN data link layer, but it's a little bit more. We want to avoid remote frames. They may cause trouble, so we don't want that. Furthermore, we start by default with a so-called base frame format. So it's the CAN base frame with the 11-bit CAN identifier. CAN-open is very tolerant. You can switch over also to the 29-bit identifier frames if it's needed, but by default, all the addressing schemes provided in CAN-open are based on the 11-bit CAN identifier. One thing to be mentioned, when you operate CAN-open, then think about the network access in CAN. So in CAN, we have message addressing. Any CAN message comes with a network-wide unique CAN identifier, identifying the data and providing the priority of the CAN frame. The lower this number, this CAN ID, the higher is the priority. And if several CAN messages compete for bus access, always that message gets the access that has the lowest number, the highest priority. Keep this in mind when you operate CAN-open systems. The reason is, when you operate CAN-open, you take care about the bus load management. All the messages have to get access to the bus in their timing requirements. CAN-open provides some means for bus load management so that you can guarantee the timing restrictions of your system, but you should have this in mind. Well, what is now CAN-open? CAN-open is not just how to use the CAN frame, but CAN-open brings you also an entire device architecture. This means, on the one hand, it gives you guidelines how to communicate via the CAN, how to run the CAN interface. So therefore, we have several services for data communication, communication of process data in broadcast, the so-called process data object, the PDO, and the service data object introduced for diagnostic purposes, for configuration purposes, allows point-to-point communication on the broadcast medium CAN, and every access is concerned by the communication partner. And you have a lot of services that are more or less network management oriented, so how to achieve a synchronous network behavior, how to adjust the unique network time, how to distribute device internal errors, you have an emergency message, and you have something strongly related to network management. You have a network management state machine for every CAN-open device that allows you to switch a CAN-open device into a configuration state, into a running state, or into a state where it's logically disconnected from the network. So, this is the way we communicate. Then we have an application software. This is more or less the core competence of the device manufacturer, how to run the drive, how to handle the metering chamber of your sensor. But now there remains, how can these two software entities exchange the information, exchange the data? And therefore, we have a device internal database. It's called the CAN-open object dictionary. And in this CAN-open object dictionary, we have a segment where we have the communication parameters. These communication parameters determine how does my device behave here at the CAN interface. And the application parameters, they may be either proprietary or standardized in SIA device or application profiles. How does my device perform here at the so-called process interface? So the process interface, this summarizes the interface to the real device application, to the metering chamber, to the drive unit, or my typical analog I/O line for my own module. Yeah. You can access via the application locally this database. You can access this database remotely. So via the bus, via the corresponding communication services provided by Canova. And this means as soon as you have access to the subject dictionary, you have full control over your Canova. So you see here a short summary how this object dictionary looks like. We are using a 4-digit hexadecimal address to reference to our data. So that's what I have now explained. Our communication data is summarized in the index range 1000, the application data in the index range 2000 to 9000. And as I've said, it coexists in any general device, the manufacturer-specific area as well as the standardized area. So it's up to you as a device manufacturer to say, do I like to communicate proprietary data with the means provided by Canova, or do I like to increase the degree of standardization of my Canova interface by following a SIA device diagram? So, you see here a closer look where I find some information, and here I just like to remind you always, when you like to change the communication behavior of your Canova device, then go to the index range 1000, and there you find the related parameters. So you see here an SDO parameter set, a PDO parameter set. If you want to modify here something, how you communicate process data, how you communicate configuration data. Here you find the parameters. Here you have a little bit granularity that you can see for further communication objects like certain times, emergency, you find where in my device do I get the information. So here we see how does CAN notation provide the information in SIA specifications or vice versa. How can you get the information where in my device resides data, resides information. And in SIA specifications, either in SIA 301 or in all the profiles, we highlight the index, where do we refer, or how do we refer to this data, right? A kind of pointer to where in my device, in my memory cells, will I find something. Then we provide a name that gives you already a link to the functionality. So, like here, 1080, oh, this is somehow the identity of it. It provides me something about the identity of the device. Then, how does the information look like I'm pointing to? Is it a single variable, or is it a group of variables, the same, or is there a data type, an array or letter? What is the data type of this object? And some information for the device manufacturer. What about the category? Is it mandatory for him? Is it an obligation for him to implement this? Or is it just an optional coupled to certain conditions? And this we provide not only for single variable, but for any data element of an array or a record, the name, the entry category, and then the information. How can we access this kind of data? So therefore we stay in the network, and from this point of view we are looking at the device and saying, is it just readable, writable, is it read-write value, or is it maybe a constant value never changing during system runtime? Very important, the value range. What is a valid value range? What is an invalid value range? What are maybe specific indications that the sensor is broken, that the sensor has erroneous value, for example? For digital values, we provide here a split of the value into bit fields and which bit is switching which kind of functionality. And finally, we provide default values. What is the default value in CAN automation understanding? This is typically a safe power-up value, a safe start value. And usually for read-write or write-only values, where I say I power on the device and now I have a value which I get out of the network, but how shall I behave with regard to this data till I get the first time out of the network this information? And for this duration, from powering on the device till I get the data, then we provide the same startup value as default value. Yeah, in Canopy we have 3 mandatory parameters in our index range for communication parameters, in range 1000. And one important is the index 1000. It's a so-called device type. It gives you the information which SIA profile has been implemented and which functionality out of the SIA profile. So these profiles are as scalable as Canopy itself, providing a lot of functionalities, and it's then up to you which function is really implemented, and you can highlight this in additional bits of this 32 bits. The lower 16 bits indicate the profile number of the implemented profile, the upper bits indicate which functionality has been implemented. For more complex devices, you have then the possibility to implement several profiles. Sounds first of all a little bit crazy. How do you do something like that? Or why do you do something like that? This is typically for very complex devices where you say, I want to encapsulate complex tasks, and this complex machinery or machine module, I like them to monitor and control sliding influence from a higher perspective. Therefore, I hide a lot of functionality in this complex module, and I can have a modular software approach, and the software approach is then supported by several implemented profiles. Up to 8 profiles we can load in one Canopy device. Maximum, a minimum, there can be just no profile. So this would be then a Canopy device communicating manufacturer-specific information with the means of Canopy. So why do we need Object 1000? For example, for doing something that is called a network scan, I make a read access to theoretically all 127 Object 1000, and when I get responses, I know, okay, at this node ID, there resides a device. If I don't get a response, then okay, there does not reside any device. And with the responses, the evaluation of the responses, I get the idea at which node I need resides in my system, which kind of functionality. In the same way, I can use the Object 1001, read all detected devices, Object 1001, and I get an idea what is the current status of these devices. Are they either in an error condition, yes or no? So the emergency state machine of Canopy device is a very simple one with an error-free state and error return state. So the device is error in an error state or not. And this we can read in Object 1001, and therefore we can, with a simple scan, get an idea of what is the current status of my system. And finally, we have then the Object 1018. This provides the information about the identity of the device. Who is the manufacturer, the vendor ID, which is provided by Canon Automation, and optionally product code, division number, and serial number of the device. So when do we need this object? In particular when it comes to dynamic node ID assignment. Because think about the use case that you have several devices in your system and you want to distribute unique node IDs to the devices, but you cannot address them by the node ID because this is your task you want to do. You want to assign node IDs. So how can we distinguish between several unconfigured Canopy devices? And then it comes back typically to the information posted in this object that we say, okay, Canon Automation distinguishes between the Canopy vendors worldwide. A single vendor distinguishes between products via the product code, revisions via the revision number, and every candidate of a revision with a serial number. And therefore, if you see the summary of this 128 bits, this is a worldwide unique address for a Canopy device. And this you can therefore use to address a device. You can say the device from that vendor with this product code, revision number, and serial number. This will get the dedicated node ID, maybe the node ID 5. So, therefore, don't underestimate this parameter. With regard to the data model we see here, Canopy introduces the device model. So software, the protocol stack for controlling the CAN interface, and very complex devices, like for example, they are used in laboratory automation. They may have the time to pipette control, move the pipette into space in several axles, and doing some aspiration and dispensing. So if you do so, you just want to control the device on the high level with pipetting control commands. But we see here also, if this comes to configuration, diagnostic, you want to always see all these details, then you have a very modular software approach, typically the application software for all the axles, for the pipetting and so on. And the approach that you can implement several device profiles, we have here also the possibility here implementing device profiles, also providing them in the application area. Up to 8 you can provide in one level. In the remaining time, we have just a brief look on the protocols, how do they work, which are necessary, which are mandatory for every Canopy device. One is here the degree of scalability. Canopy provides 2 types of services for data transport, for the process data, the video, the process data object, for configuration, diagnostic purposes, the service data object. The service data object allows access to any object dictionary entry of a Canopy device, transfer any data element in this object dictionary independent of its size, and you get always a confirmation. When you run something, you get a confirmation, yes, I've accepted the data, it's successfully written, or vice versa, if I want to read it, I get the data, or I get an abort response that indicates, for this or that reason, you cannot fulfill this transfer. We have several types of SDO transfer, the segmented one, we have an accelerated one, the expedited for very small data packages not larger than 4 bytes. We have the block transfer for big data packages, and then we have all the services for data transfer. And as I've already said, some special protocols for synchronization, timestamp, and emergency. Don't underestimate the emergency service that helps you enormously in terms of diagnostics. And you have then the network management to switch the device into configuration state, logical disconnection or running state, the boot up message, hey, I'm here, I'm ready to work. This is a registration message, and some monitoring service, the error control protocols. Here we recommend for new implementation the heartbeat service that indicates, okay, the device is still there, it's still in the current network state, and it's still operating. So let's just have a brief look on some of these communication objects which you lack of time. I think it's very important that you understand how this service data object works. The service data object establishes a point-to-point communication on the broadcast medium CAN. So you take 2 CAN data frames, you reserve them by means of the network-wide unique CAN identifier, and you say, okay, I have now the situation, I have 2 devices, 2 Canopy devices. The one has an interest to read or write something at the other device, so that one that has the interest in reading or writing, this is called the SDO client, and the other one that is accessed by read or write access is called the SDO server. And then we say, okay, we learn that the devices this pair of CAN identifiers and say, okay, if you want to read or write something in the dictionary of that device, use this CAN ID, the CAN message with that ID, and we say expect the answer in a CAN frame with that ID. And vice versa, to that device we say, if you see ever a CAN ID with that compares to this N, then it's a request for your object dictionary, process this request, and provide the answer with that CAN frame here. And therefore, we succeeded in establishing a point-to-point communication by using 2 CAN data frames. They are determining who is talking to each other, and who is the client, and who is the server. And this I need for any cross-communication in CAN. If 2 devices shall communicate with each other in a confirmed way in this by means of SDO, then we always need a pair of CAN identifiers. Double check which pair of CAN identifiers is free, which pair fits from the priority, and then reserve it, assign it to your two devices that shall talk to each other, and then they can use it. So from a data point of view, all devices connected can monitor this communication. You can trace this communication with any data logger, but as soon as you have an open interpretation, only these two devices will communicate. Now we know we can open up a communication channel, we know how to carry the data via these containers in the message N and the message P. Now we need to fulfill the data content, and the data content looks like that. We say, okay, we have to initiate an SDO, we have to tell the server, hey, we want to read or write in your object dictionary. Which index and subindex in this object dictionary shall be accessed? So we see this here, index, subindex is the multiplexer. And then the server can double check, am I capable to handle this transfer? And then he gives me the confirmation. And now I'd like to remind you a classic can frame has the capability to carry up to 8 bytes of data. For this command specifier, we need 1 byte of data. For index and subindex, we need 3 bytes of data. This means we have used 4 bytes of data of our 8 byte can message. And this means if the data is not larger than 4 bytes, can open allows me to transfer the data directly within the initiation. And if I do so, I will indicate, hey, we are using the expedited transfer. I think this is the most commonly used transfer in Canova. This depicts the write access, the read access, and you see I get always the confirmation, okay, the data successfully written, and also the confirmation includes to which index and subindex in the object dictionary of the server has the data been written. We see here the segmented transfer, also initiation. We want to write in this example something maybe to index 3000, subindex 5. I can provide the length in multiples of 1 byte. And I get the confirmation, and as soon as I have it as a client, the confirmation, I open up a kind of ping-pong game. Here's the next segment, okay, the next confirmation. And we see per segment we can transfer up to 7 bytes of data, and we indicate in the command specifier whether this is the last segment or whether there are further segments following for the terminate and the confirmation. Every SDO transfer is confirmed, but sometimes we don't like the confirmation because it's an abort transfer, indicating us, oh, there was something wrong. So even in Canova we can have errors or system problems, and in this case, maybe we would say, okay, you tried to write something that's out of the value range, or you tried to write a parameter, but this is read-only. So then I get the abort message, please client, change your behavior, and then we can proceed. Always you want to learn that the two devices shall communicate with each other via SDO, then you need to go to the SDO parameter sets. As I've said, communication behavior is always modified in the index range 1000. So the segment 1200 and following, these are the so-called SDO parameters. The first part dedicated to server parameters, the other one to client parameters. So server parameters, my device shall take these can identifiers as requests to its own object dictionary and the request to provide the answer, or here I provide as client parameter the can identifier so that my device knows, okay, if I shall access another device, I use this can identifier for my request and that can identifier provides the answer. Every can open device comes by default with a so-called SDO default server channel. This means 600 plus my own node ID as a can identifier. I expect the request and I provide in a 580 plus my node ID to answer. What does this mean? I just have to adjust a unique node ID of the device, switch on the device, and this channel is valid, and I can use it and can access any device via this channel. So, just to give you an idea how this channel parameters works, you have maybe your first the server channel address in any canonical line 600 plus my node ID expect the request with a 580 plus node ID I provide the response. So this means I double check that I have in my host controller a client functionality available. This is an invalid one maybe. Then I come with my configuration tool, configure it, and say, okay, I mirror somehow the behavior of the service. Say if I need to have a communication channel to let me write during system runtime, make it equal to the 610 and provide the answer to 509. All this I do in the STO parameters. What about video communication? A video becomes always in broadcast up to 8 bytes of data between a front user and several consumers. So I can have here a multicast or broadcast communication, depending on my setup, up to 8 bytes of application data. So on the one hand, great, in contrast to the SDO, a single frame I can use up to 8 bytes of data, but how to interpret that data? And therefore, I need big tables and can open. These are the so-called video parameters. One video is determined by a pair of parameters. It's the communication parameter and the mapping parameter. So we see here this big index table for configuring videos. We distinguish between the receive direction and the transmit direction. And for both of them we have communication parameters and mapping parameters. The communication parameters say which CAN identifiers are used, which triggering event is used to communicate this data, bus load management features, when can we send this data, when is it allowed, or how often is it allowed to send this data, and vice versa, the mapping, how does the data content look like. And we see here a summarization of all of that. For example, if I want to receive data, I see, okay, I have to adjust it in the corresponding parameter set, 1400 subindex 1. Here I have my so-called POP ID entry, simplified a CAN ID, which CAN ID I like to trigger on, which CAN message I like to receive. So we see here, if there comes such a CAN message, then my protocol stack will see, oh, CAN identify what and one, what's that? Ah, this is somehow familiar. It's here in my communication parameters of the first received video. I know this, and the related mapping table is then at 1600, and then I can say, okay, now I can interpret this data. Let's take the first 8 bits, map them to 2000 subindex 1. Okay, now I know this is a temperature value. Then I take the next 2 bytes and map them to 2003 subindex 3. Oh, this is a depth value, a millimeter. And then I take the last 8 bits, map them to 2003 subindex 1. This is a H value in millimeters. So thanks to this mapping table, I can now interpret the data communicated in a CAN open video. And third-wise, I can theoretically at least configure up to 512 videos and receive and transmit direction. For default, by default, I get 4 CAN identifiers for receive and transmit direction, but we will see later on there exists a possibility to adjust further CAN identifiers in the device. Yeah, so much with regard to the videos. We have also, as I've said, special communication objects. The SIP protocol allows you a synchronous network behavior. You have also the possibility to provide a counterbind to allow good synchronous adjustment between several devices. So I can say you shall send the SIP 1, SIP 2, SIP 3. So typically the SIP is used for bus load management, to keep a stable bus load all over the network. We have the emergency protocol. The emergency protocol allows you to communicate via internal errors. So we can find error information in the emergency error code. Maybe we are counting the error passive state, we have lost data in the CAN container. And furthermore, the device manufacturer has the capability to provide some manufacturer-specific error information. If a device is capable to transmit error information, we see here if the object 1014 is supported, and furthermore, it makes sense if there's anybody outside the network that is interested in this emergency message. This is a so-called consumer functionality, and therefore there's the possibility of having an array where I can adjust from which device I like to receive the errors and to start some countermeasures. You get here an idea how these errors could look like, that could be communicated by a device. We are operating in the wrong power supply, we are operating in the wrong temperature range, or we have some communication errors. So, very important is the state machine. Every open device has a state machine that allows switching a device in a configuration state, in an operational state, or in a stop state. So when I switch on a device, it applies the node ID, the bit rate settings, and then it transits to a pre-operational state. Pre-operational state means, hey, I'm ready to work, but it's not really operating now, but it's a stage before, so giving the system integrator the chance to double check, have you configured everything correctly, or do I like to introduce some intended cross-communication between the devices. Typically, the state is used for video configurations, intended cross-communication during system runtime between my devices. When I verified my configuration coherences in the network, I switched all the devices to operational. All communication services are available. The main code will be based on PTOs. In contrast to the pre-operational services, here the PTOs do not exist. The counterpart to the operational state is the stop state. The stop state, almost no communication services are available. Just the NMT service, for example, to allow switching the device into other network states. So here we see how this NMT command looks like. It comes with NID0, 2-byte message. The first byte introduces the command, what is intended, which states which is requested, and on the other hand we have the node ID value. This node ID field indicates who shall execute this command, or there's also the option of having a root command, all devices shall use this. So, on entering the operational state, the device registers in the network and says, hey, here I am, I'm ready to work, and this is done via the root message, comes over to the 700 text node ID, 1 byte of data, the 0 is inside, and this indicates the device is ready to work, is potentially in the operational state. And the same telegram is used for the final service, the heartbeat service. Here you have a time, the so-called heartbeat time. You can set a cycle time, and within the cycle time, every second the device registers in the network and says, hey, here still I am, and I'm working in this or that network state related to the status in the network management state machine. So these are the open services. You see a lot of communication coherences that you can set up on the CAN data link layer. And finally, I'd like to mention these CAN identifiers. We saw already a broad range of CAN identifiers that are used sometimes, sometimes not, and we can extend them. And therefore, I'd like to introduce this predefined CAN ID set, how it is depicted also in the CAN open specification. And what's the purpose of this ID set? It's not to describe a fully meshed CAN open network with up to 127 devices. But the purpose is to say, okay, we need to have a clean system when a system designer has purchased several devices, has assigned a unique node ID value, has adjusted a common bit rate, then this system designer shall plug the devices to the same cable, power them on, and then we shall experience a clean bus where I have no misinterpretation between the devices, no device should interfere another device, no device can listen to another device, and the system integrators will now have all the tools to establish independent cross-communication. And for this purpose, we have this table, and it provides a subset of communication objects, and T comes always to the zero. Sync, timestamp, emergency, 4 PDOs in receiver transmit directions, this first STO server channel through the heartbeat. We allocate to them a certain offset, and typically in conjunction with the local node ID, we get the pair identifier that shall be used for the service by default. And as I said, NP comes always with a zero, no dependency for local node ID. Sync timestamp optional services come by default with 80 hex and 100 hex. You can change it, you can modify it, they do not depend on the node ID. You can also have several sync mechanisms for several purposes in your system. But this is a system configuration. Emergency comes always with the 80 hex plus node ID of the producer. I would strongly recommend to keep that because it's very convenient for diagnostic to say, okay, we have the 86, the device with node number 6 has a problem. Videos, 100, 180, 280, 300, 480 hex plus node ID of the producer. For the receiver, vice versa, 200, 300, 400, 500 plus node ID of the receiver. So when you evaluate this very carefully, you will see no transmit video is matching to a single receive video. It's then up to the system integrator to establish intended cross-communication. And here we see the first STO server channel, 580 plus node ID of the server. We respond to the request that comes from the 600 plus node ID of the server. Boolean heartbeat, 700 plus node ID of the producer of the heartbeat. Yeah, as always said, we have got an open performance testing, so we offer this at Plan Automation Office, the performance test. You can also download as a Plan Automation member the performance test for producer evaluation. There's my implementation matched with the implementation of the open specification. And finally, I like to highlight that one of the purpose of a device performance, we have now seen we can communicate data with an open in a point-to-point communication, in a broadcast communication, or a video. But how can I get now the first 82 inputs of my I/O model? Then I have the device profile. Device profile says where does my process data reside? For example, where reside my first 82 inputs, index 6000 subindex 1. So you can give me any I/O module. I have never seen this before, but I know exactly where I get the process data. And I can get it either via STO access, or if the node ID wants adjusted to this device, I wait for a pair message with a 181, and I evaluate the least significant 8 bits, and I know here's the status. How to hand over this upgrade data for being applied to the output, 6200, subindex 1, write access, and that's it. So, if you follow the point that my application profile is degree, this is the degree of standardization of your Canon device graphically, as it standardized also the application data in addition to the communication, and it uses, of course, the plug-and-play capability of your device. Yeah, so much as small and fast ride to the world of Canon. So as Oliver has reported with regard to Ken, you could go an entire day about this, the same as well as the basic Canon. Nevertheless, I hope I could touch all the important points of Canon, and then I think we have reached lunchtime, but maybe there's one or two questions left. So you're hungry, you want to have lunch. Okay. Maybe we can solve them during lunchtime. Thank you. So any